Ever been to a fun house? You know those crazy mirrors that make you look all stretched out or squished?
Yeah. Yeah, I know exactly what you mean.
Well, that's kind of what we're looking at today. But instead of our bodies, it's like the whole room is warping.
That's a pretty good way to visualize it, actually.
We're talking about eigenvectors and eigenvalues,
Exactly.
and they might sound intimidating,
Yeah.
but they're really just about understanding how things change.
And how some things stay the same even when everything around them is changing.
Right. So let's break this down.
Okay.
First off, when we say transformation, what does that even mean in this context?
It's a way of changing something mathematically, whether that's its position or size or orientation.
So like, I don't know, rotating a picture on your phone,
Yeah, exactly like that.
or stretching a rubber band, or shrinking something down.
Precisely all of those are transformations.
Gotcha. So we're not just talking about physical objects then, right?
No, no, not at all.
This applies to anything we can represent with math,
Exactly.
which includes vectors. Okay, so vectors, they're kind of like arrows, right?
Yeah, they have a direction and a length.
And when we apply a transformation to them, it usually changes their direction or length or both.
Usually, but sometimes there are these special vectors that don't change their direction even when a transformation is applied.
Hold on, so even if everything else is getting all distorted, these special vectors stay on the same path?
That's the idea.
No.
They might get longer or shorter, but they'll keep pointing the same way.
Wow, that's pretty cool.
And we call these special vectors eigenvectors.
Eigenvectors, okay.
And the amount they stretch or shrink during the transformation is given by its eigenvalue.
So the eigenvalue is like a measure of how much the transformation affects that particular eigenvector.
Exactly. It tells you the scaling factor, how much bigger or smaller it gets.
Okay, I think I'm starting to get it. So we've got these eigenvectors that hold their direction, and then the corresponding eigenvalues tell us how much they're stretched or shrunk.
You got it.
And the amazing thing is that this isn't just some abstract math concept.
Oh, definitely not.
This stuff is used in so many different fields.
From physics to computer graphics to data analysis, you name it.
Really?
Yeah.
So we're talking real-world applications here.
Absolutely. They help us analyze and simplify all sorts of complex systems.
Okay, I'm definitely intrigued.
Yeah.
So how do we actually find these eigenvectors and eigenvalues? Is it like a super complicated process?
Well, it involves a bit of linear algebra,
Ah, linear algebra.
but the basic idea is that we start with a matrix that represents our transformation.
A matrix,
Oh,
like
yeah.
a grid of numbers.
Exactly.
Okay.
And we use some mathematical tools to find the eigenvectors and eigenvalues of that matrix.
So through some calculations, we can figure out those special vectors that stay on course and how much they change.
That's right. And once you have those, you can unlock all sorts of insights about the system you're studying.
Okay, this is way cooler than I initially thought. Tell me more about these real-world applications.
All right, let's dive in. Okay, so imagine you have this system that's changing over time, like our funhouse mirror room.
Gotcha.
Now, within that system, there might be some parts that are more important than others in terms of understanding how the whole thing behaves.
So like some parts of the room are stretching a lot more than others?
Exactly. And eigenvectors can help us find those key directions, the ones that are really driving the change.
Interesting. So it's not just about how individual vectors are affected, but about what those eigenvectors tell us about the whole system.
That's a great way to put it. It's like they're the pillars of the system, the things that really matter.
And the eigenvalues tell us how much those pillars are being stretched or squished right.
Exactly. A bigger eigenvalue means a bigger change along that eigenvector.
So a big eigenvalue means that direction is really feeling the effects of the transformation.
Exactly. And by looking at all the eigenvectors and eigenvalues together, we can get a really good understanding of how the whole system is changing.
So it's like we're getting a simplified view of a complex system by focusing on these unchanging directions.
Precisely. And it's not just about describing the change, it's about understanding it.
What do you mean?
Well, by analyzing the eigenvectors and eigenvalues, we can learn about things like stability and dominant behaviors.
Okay, this is starting to sound a bit more abstract. Can you give me some concrete examples of how this is used in different fields?
Sure. Let's take physics, for example. In quantum mechanics, the state of a particle can be represented by a vector.
Okay, so we're not talking about stretching rubber bands anymore.
Right. We're talking about changes in a particle's properties, like its energy or momentum.
Got it.
And when a particle undergoes a transformation, like interacting with another particle, the eigenvectors tell us about the particle's stationary states, the ones that don't change over time.
So even in the quantum world where everything is kind of fuzzy, we can still find these stable states.
Yeah, exactly. And the eigenvalues in this case represent the energy levels of those states.
So we're talking about the fundamental energy of a quantum system.
Precisely. And this idea of finding the unchanging directions pops up in other fields too, like data analysis, for instance.
In analysis.
Ah,
Okay, so now we're switching gears from particles to data,
right. Imagine you have a huge data set with lots of different variables.
like trying to understand customer behavior based on their purchase history and demographics.
Exactly. That's a lot of information to deal with.
Yeah, for sure.
But eigenvectors can help us simplify things. They let us find the most important dimensions of the data, the ones that explain the most variation.
So instead of trying to look at hundreds of variables, we can focus on the few that really matter.
Right. And this is used in all sorts of applications like facial recognition and recommendation systems.
Wow, so eigenvectors and eigenvalues are like this universal tool for understanding change in all sorts of different systems.
That's what's so fascinating about them. They point to a deeper truth about how systems are structured and how they behave.
Okay, now you've really got me thinking. What do you mean by a deeper truth? You were saying there's this deeper truth about how systems are structured and how they behave.
Yeah, think about it this way. If we can find these unchanging directions, these eigenvectors in all sorts of different systems,
Right.
like from tiny particles to massive data sets, it kind of suggests that there's something fundamental about how change itself works.
So it's not just a coincidence that these eigenvectors keep popping up everywhere.
It seems like there's this underlying structure, this mathematical blueprint that governs how things transform and evolve.
And eigenvectors are giving us a glimpse into that blueprint.
Exactly.
That's a pretty amazing thought.
Yeah, it is. And it has implications that go way beyond specific examples.
Like what?
Well, it suggests that there might be universal principles governing how systems behave, principles that we can uncover by studying these eigenvectors and eigenvalues.
Wow, this has been quite a journey. We started with funhouse mirrors and ended up talking about the fundamental nature of change.
It's funny how these seemingly simple concepts can lead to such profound insights.
I'm definitely leading with a whole new perspective.
I'm glad to hear that.
Thanks for taking the time to break all of this down for me.
It's been my pleasure.
And to our listeners, thanks for joining us on this deep dive into eigenvectors and eigenvalues. We'll catch you next time.